Good morning, class. The session is being recorded, and again, for privacy issue, please mute your audio video. And when I ask you to participate, you don't have to participate if you don't want to. So we are looking at the derivative of a log functions. We have covered a few sections, and we also covered the second part of section 3.5, the chain rule, which had the implicit differentiation and related rates. Now, there are many differentiation formulas that hopefully everybody is comfortable with, okay? And we need to be comfortable with it to move on. Also, a lot of logarithmic properties. You've seen it in algebra, so I want to, touch upon that, starting with the definition. Okay. When we see the log, we should recognize the base, we should recognize the exponent. Okay. And if we can go from one format to the next, we would have absolutely no problem. Now, the restriction is the base cannot be 1 and must be positive. Okay. Now, just to refresh your memory about the concept, log is simply an exponent. So just as an example, if somebody asks us 5 to what power is 25, it is the same as what is log 25 with base 5? And both have the answer 2. Okay, everybody? That is extremely important. Now, there are some properties in general for logs. So let's quickly discuss them. Log 1 with any base is 0 because b to the power of 0 is 1. Log b base b is 1 because b to the power of 1 is b. In other words, when the argument and the base are the same, the answer is 1. These two refer to the fact that logarithmic functions and exponential functions are inverse functions. Okay. Product rule, quotient rule, power rule. We should be very comfortable with that. And down here we have what's called the change of base formula, meaning if you're interested in evaluating log x with some base, we can use log x over log b and choose any base such as a, or if we don't write the base, becomes a common log, the base is 10. Or if we use ln, it becomes a natural log, the base is e. Now, knowing this general format, we should be able to go to these two and write it for common log when the base is 10 and a natural log when the base is e. I hope you're comfortable with those, okay, class? In the case of a common log, you just drop the base b. The only thing you want to be careful of is here. It is log 10, which is 1, okay? And log 10 to the power of x is x. 10 to the power of log x equals x. Those are the two that you want to be able to handle, okay? In other words, okay. And so what that means, logarithmic functions and exponential functions are inverse functions. Therefore, when we look at this graph, y equals e to the power of x and y equals ln x, they are inverse functions. And if we graph them, they are symmetric with respect to the line y equals x. Okay. All right. I want to go over a couple of questions that I expect you to know we are not going have questions like this for the exam, you are supposed to know. I just want to remind you how we arrive at the answer. For example, log 81 base 3 is equal to 4 because 3 to the power of 4 is 81. Now, the way we did that in algebra, I'm going to go over that. We said log 81 base 3, we don't know what that is. And we wrote, look at the arrow. We wrote the exponential form. The base is 3, the exponent is x, and this is 81. And because 81 is 3 to the power of 4, you know the answer is 4. Okay, class. Log 5 base 25 is 1/2 because 25 to the power of 1/2 is 5. Or we could write log 5 base 25 is missing. I'm not going to use the x, I'm going to use something else, let's say y. And then by exponential definition, 25 to the power of y is equal to 5. We also know that 25 is 5 squared. So we have 5 squared to the power of y. That means 5 to the power of 2y is equal to 5. The exponent is missing here, so this must be 1. 2y equals 1, y equals 1/2. Part C, log of 0.001, there are 3 decimals, so the answer is -3, or you can say because 10 to the power of -3 is 0.001. For common logs, when it ends with 1 and a bunch of decimals, you just count the number of decimals and you go with negative. However, if you have 1 with a bunch of zeros, then you count the number of zeros and make it positive. Log of 10,000 is 4. Okay. All right. Let's go with the exponential form of the logs. We want to rewrite each and every one of them in an exponential form. Okay, everybody, so let's do that. Can anybody tell us the first one? Anybody? I mean, again, you don't have to participate, but if you like and you don't mind. How would you rewrite this in an exponential form? Look at the arrow that I'm going to put. 5 to the power of 4 is 625. The second one?
7 to the power of 2 is equal to 49.
Perfect. Next. Look at the arrow.
1/3 to the power of -4 is 81.
Perfect. Next one.
81 to the power of 1/4 is equal to 3.
And finally,
1/2 to the power of -5 is equal to 32.
perfect. So I hope you see it's pretty simple. If we can go from one format to the next, it makes life easy. All right, so there were some basic questions. Hopefully everybody is comfortable with all of them. And so we can move on and do calculus now. So 1/2 to the power of -5 is 32. Okay. We're going to take the derivative of y equals ln x. We don't know how to do that yet, but we do know the exponential, so we are going to rewrite this in an exponential form. By the way, class, you can write it as equals y and go this way. That means, of course, when we don't write the base with ln, the base is e. And so the derivative of e to the power of y is itself times y prime or dy dx by the chain rule, and the right side x gives us 1. So y prime is 1 over e to the power of y, which is x. We just proved the derivative of y equals ln x. You just flip it over, is 1 over x. Therefore, we're going to write the derivative of ln x is 1 over x in an absolute value, because I hope you remember the domain is 0 to infinity for ln x. If you put u, where u is like g of x, is a function of x, you flip that over based on this, you flip it over, and then by the chain rule times the derivative of this guy, du dx. So if it's g of x, flip it over, times the derivative, which is g prime. So let's look at a few examples. We want to differentiate y equals ln of 5x minus 1. So basically, we flip this over, we get 1 over 5x minus 1. 1 over 5x minus 1. And by the chain rule, we need g prime. We need the derivative of the parentheses, which is 5. And we just rewrite it. And we are done. Flip it over, multiply by the derivative of its argument. All right, for a case like number 2, there are 2 ways to do that. And I'm going to do both ways because this is simple enough, doesn't make much of a difference. So let's go over the 2 methods, then I'll tell you which method you want to use more often. So just the way it is, ln of x cubed. So flip that over. 1 over x cubed. 1 over x cubed. And we need g prime. We need the derivative of x cubed, 3x squared. Done with calculus. Simplify. You get 3 over x and you're done. However, we've learned so many logarithmic properties, we can simplify it first. And as I mentioned, in this case, doesn't make that much of a difference. That means from here, put the 3 in front using the power rule and write it as 3 ln x. So do algebra first. So what is y prime? 3 times 1 over x. Okay, so let me write that in case. So y prime is 3 times 1 over x, okay? Which is 3 over x. And as I mentioned, it doesn't make much of a difference in this case. The more complicated the log, the faster the second method. So you want to know how to decompose a log completely using properties of logs. Here's an example. How would we decompose this class? That's what you want to ask yourself. Because if we don't decompose it, you have to flip this over. So it's a fraction, flip it over, you get a new fraction, and then differentiate that using the quotient rule. Is it doable? Yes, but it takes longer to do it that way. Instead, we are going to decompose. You can do it in 1 or 2 shots. Anybody knows how to do that? Decompose this completely? Class? Anyone? Quotient rule, ln of the top minus ln of the bottom. And of course, I expect you to do this in 1 shot. ln of 2x is ln 2 plus ln x. So we did our algebraic technique. Now, piece by piece. This one is a number, gives you 0. This one gives you 1 over x minus. This 1 over 2x plus 1 times 2. And again, don't forget that this gives you 0, okay, class, because it is a number. And so you are dealing with 1 over x minus 2 over 2x plus 1. You take a common denominator of x times 2x plus 1. 1 times 2x plus 1 minus 2 times x. 2x cancels out the negative 2x. And here's your final answer. So, a quick recap. Do your algebraic techniques to decompose this first. It makes it easier. Then here's your only calculus step.
Wait,
Algebra. Go ahead.
Professor, can you explain where you got the 2 from?
Where we got this 2 from?
The 2, yeah, that one.
Okay, g prime of x. This is minus. Flip this over, right? Times g prime of x. That means the derivative of 2x plus 1. That's where the 2 comes from, by the chain rule.
Thank you.
My pleasure. Okay, class. So again, algebraic techniques using logarithmic properties to decompose. 1 by 1, ln 2 is a number. The answer is 0. ln x is 1 over x minus, so the sign remains. Flip this over, 1 over 2x plus 1. And now by the chain rule, you need the derivative of 2x plus 1, g prime of x. This is g of x. The derivative of 2x plus 1 is 2. And then you put them together using your algebraic techniques and finish the job. To do this, you can use a product rule just the way it is, but it is easier if you rewrite this by putting the 2 in front as 2 ln x. So if we change this to 2 ln x, everybody, now we have 10x times ln x. We have a choice of saying it's 10x times ln x and do the math, or we can just ignore the 10 as a multiplier. Eventually, we have to factor it out. Either way is fine. Either way is fine. (10x) gives you 10 times ln x plus ln x gives you 1 over x times 10x. Okay. And I hope you see that this cancels out this one. You have 10 ln x plus 10 10 ln x plus 10, we can take a common factor of 10. All right. Please note that ln x is in the numerator and the denominator has got nothing to do with that. Therefore, you're using the quotient rule to do the math. Okay. Because they're both x, it may be not a good idea to show what I have in mind. But if you look at this example, ln of x over y is not the same as ln x over y, okay? So don't mix them up. Okay, so we use the quotient rule class, and therefore, let me just write the quotient rule. Just remind you, f prime, this is f, this is g, f prime g minus g prime f over g squared, which means we need the derivative of the top, which is 1 over x, and then times g, the bottom, minus g prime, the derivative of the bottom is 1 times the top. Now just write this, square it. And of course, they simplify to 1. This whole thing becomes 1. So 1 minus ln x over x squared is the final answer. Okay, so quotient rule. If you differentiate this just the way it is, it's pretty complicated because you need to flip this over and then differentiate this using the product rule in conjunction with the chain rule. However, we want to decompose this. In other words, we want to do algebra. We want to use our logarithmic properties to decompose this. Can anybody tell us what is the decompose format of this guy? How would you decompose this completely? That's the first part that matters.
I'd
Simple.
say we split it so it becomes ln 3x and ln x plus 4 to the power of 5.
Okay, let me write that. So ln 3x plus ln of x plus 4 to the power of 5. So far, so good. Okay, we are not finished, class. We want to simplify this further. We want to decompose this further. How would you do that? Look at this one only. How would you do this one? Anyone?
ln 3 plus ln x.
Beautiful, because it's 3 times x. ln 3 plus ln x, done. Now, we move to the second piece. How would you do that? How would you simplify this guy?
Move the 5 to the front.
Power rule.
Yeah, power rule.
Yeah, perfect. So, 3 ln 3, x ln x. This piece, 5 sits in front. Here's the answer. Whether you take a couple of steps or in one shot, it is absolutely fine. Now it's easy to do the math. We are going to differentiate piece by piece. This is a number, everybody. ln 3, ln 2, e pi makes no difference. This gives you 0. So that's gone. ln x, 1 over x, plus 5 times. Now, how do we differentiate this? Flip it over. 1 over g of x, 1 over x plus 1. By the chain rule, times g prime. The derivative of the parentheses is only 1. So let's recap. ln3, 0. ln x, 1 over x. 5 remains. Natural log. Flip it over. By the chain rule, the derivative of the inside is 1. And we're done. We just do our algebraic techniques to find the LCD and finish the job. Now, I hope you realize this is 1 over x and this is 5 over x plus 4. So 1 times x plus 4 plus 5 times x, and the common denominator is the product of x and x plus 4. This is algebra, and you can't afford to be uncomfortable with, okay, class? I'm assuming we are all comfortable with algebra. So one more time, x times x plus 4 is the LCD. 1 times x plus 4, 5 times x. And that is x plus 5x, which is 6x, and then 4. Maybe we write this as x plus 4, and then x and 5x, they add up to 6x. All right. Here's the next one. First, let's put a raised dot in between. So we notice we are using the product rule, everybody. We are using the product rule. All right. Now, e to the power of 2x. The answer is itself e to the power of 2x times 2. By the product rule times ln x. ln x gives you 1 over x times e to the power of 2x. So again, e to the power of 2x gives you e to the power of 2x times 2. Okay, class? And as you can see, we have a common factor of e to the power of 2x. And if we take it out, we are left with 2 ln x from here, 1 over x from here, and that's the final answer. Make sure to factor the answer. Okay. The next question, we want to differentiate a log when the base is no longer e. We are not dealing with natural log. How do we do that? First, we are going to use the change of base formula. And we are going to write, when the base is anything other than e, we can write ln x over ln b, because we can write the log x over log b with any base. When we write ln x, that means our choice is natural log. Therefore, let's rewrite this actually as one over ln b times ln x. 1 over ln b is just a number, everybody. So if I want y prime, 1 over ln b is just a number. And then 1 over x gives me just 1 over x. ln x gives me 1 over x. And so y prime, okay, or f prime if you will, is equal to 1 over x ln b. 1 over x ln b. Okay. Now, what if we have a function of x? Let's go over the process. If it's f of x, we flip it over because the base is not e 1 over ln of that base. And because this is not x, f prime of x, this is by the chain rule. Okay, class? So 1 over f of x, 1 over ln b, and then f prime. As an example, when we do this, first we are going to change the square root of x to x to the power of 1/2 simplified, okay, using logarithmic properties. Now we are going to differentiate as follows. So take a look. 1/2 is just a number remains. Log x, so flip the x, 1 over x. The base is not e, so 1 over ln of whatever this number is. So one more time. 1/2 remains. Log x, flip it over, 1 over x. The base is not e, so 1 over ln 3. This is by the change of base formula, and we are going to rewrite that. 1 over 2x ln 3. You can't put the 2x after ln 3. It's awkward, okay? One may think it's part of that, for part of the argument of log. All right, let's see if we can decompose this. As we look at the question, there is nothing we can do to decompose this further, so let's deal with it just the way it is. Okay, it's a log. Flip this over, everybody. 1 over x squared plus 1. It's a log, flip it over. This is not x. This is a function of x. We need the derivative by the chain rule times 2x. The base is not e. Change of base formula, 1 over natural log of y. So let's quickly recap. Flip this over. Take the derivative, chain rule. The base is e, you're done. It's not 1 over natural log of that. Put them together, and you're done. All right. Let's also do this page. Y equals ln x, ln of sine x. Whatever this is, flip it over. 1 over sine x. 1 over g of x. 1 over sine x. Times g prime. Now we need the derivative of sine, which is cosine. And you know cosine over sine is cotangent. And we're done. Okay. How about this one? Let's decompose the log, meaning keep the 1/2. This becomes ln of the top minus ln of the bottom. There's nothing we can do to further decompose that. Let's differentiate. Okay. 1/2 is a multiplier. It's going to remain, everybody. So 1/2. Inside the brackets, 1 by 1. Natural log, flip this over, 1 over 1 plus x. Times its derivative. The derivative of 1 plus x is just 1. Minus, flip this over, 1 over 1 minus x. Times the derivative of the inside, which is negative 1. So one more time. Here's 1/2. This one, flip it over. What is the derivative of the inside? 1. Minus, flip it over. What is the derivative of the inside? Negative 1. So I'm going to show you what happens to the brackets. One over 1 plus x plus 1 over 1 minus x. I'm just looking at the brackets. And I take a common denominator of 1 plus x times 1 minus x. So I get 1 times 1 minus x plus 1 times 1 plus x. I hope you see that the numerator changes to 2. And this number 2 and this number 1/2, they cancel each other. And the numerator changes to 1. The denominator is 1 minus x squared. Here's the last one. Literally change this to g of x class because it's ln of ln 5x. So you need 1 over g of x. So 1 over g of x times g prime. So you need 1 over ln 5x, 1 over ln 5x, g prime of x times the derivative of ln 5x. What is the derivative of ln 5x? Is 1 over 5x times 5. I hope you see that. The derivative of ln 5x. By the way, you could write ln 5x as ln 5 plus ln x, but it makes it more difficult. It's easier to just continue the way it is. This 5 cancels out this 5. So the numerator is 1 and the denominator is x times ln 5x. X times ln 5x.